Which of the following physical quantities is not a vector? Well, if it is not a vector, then what is it? It is a scalar, a physical quantity that has only magnitude and no direction. Let's look at our options. 1.1, we have distance. We know fully well that distance is a scalar. So the answer to 1.1 is A, because distance is not a vector, it is a scalar. Force is a vector, velocity is a vector, and acceleration is a vector. Let's look at 1.2. In the equation, Vx is equals to Vi delta t plus a half A delta t squared. Vi delta t represents what? Let's look at Vi delta t and make sense of it. Vi, that is the velocity. So we have velocity, and then delta t is the time, obviously. So we have velocity multiplied by time. Velocity multiplied by time gives you what? It gives you displacement. Velocity multiplied by time, it gives you displacement. So the answer to 1.2 is D. The answer to 1.2 is D, because Vi multiplied by delta t will give you the displacement. Let's look at 1.3. Which of the following is obtained by calculating gradient of displacement versus time graph? Displacement versus time graph. Displacement versus time graph. If you calculate the gradient of displacement versus time, you will get velocity. And if you calculate the gradient of velocity versus time, then you will get acceleration. So the answer to 1.3 is velocity, which is B, which is option B. The gradient of displacement versus time is velocity. If the question was saying velocity versus time, the gradient would give us the acceleration. Let's look at 1.4. In 1.4, in the diagram below, a pendulum bob of mass m is released from point A and swings past points B, C, and D. Ignore all effects of air resistance. In which of the following position will the value of the gravitational potential energy of the pendulum bob be the smallest? So what is gravitational potential energy? It is the mass multiplied by the gravity multiplied by the height. The mass is gonna remain the same, obviously. Gravity is gonna remain the same. So we're interested on the height. The smallest height will give you the smallest gravitational potential energy. So let's go and find out at which point is our height the smallest. A seems like it's our highest point, and then B and also D. As you can see here, the smallest height is at point C. At point C, that's where we have the smallest height. So the answer here would be option C, because that's where we have C, right? The gravitational potential energy is the smallest where the kinetic energy is the highest, and that is at point C. Let's look at 1.5. 1.5, the number of sound vibrations per second. That is the frequency. So the answer to 1.5 is actually B, because we know that frequency is equals to 1 divided by the period. The number of vibrations per second, the number of wavelength that passes a point in a second. Option B, the frequency. Let's look at 1.6. So in 1.6, we have two identical spheres, A and B, on insulated stands that carry different charges. The spheres are brought into contact and separated again. If the charge on sphere A after the separation is Q, the charge on sphere B after the separation is. So if you bring two spheres into contact and you separate them, the new charge is going to be Q nu, that is equals to Q1 plus Q2 divided by Q. So you can see from this formula that the charges on the two spheres after bringing them into contact and separating them should be the same. So if we're saying that the charge on sphere A is Q, then the charge on sphere B after separation should also be Q. So the answer to 1.6 is B. 1.7, we have a circuit diagram given to us. The question is saying, what is the voltage across the parallel resistors? So our battery, our total voltage is 7 volts. And then we have a resistor here that is dissipating 4 volts, another resistor with 1 volt. So we know fully well that, so let's say 1.7, we know fully well that VT, the total voltage, is equals to V1 plus V2 plus V3 and so on. V1, V2, V3 being all places where voltage is dissipated. We're looking for the voltage across the parallel resistors. We're looking for the voltage across the parallel resistors. So VT, the total voltage is 7 volts. And then here we have 4 volts being dissipated. So we're going to have 4 plus 1 and then plus the voltage in parallel. So this will be 7 equals to 5 plus Vp. If you take 5 to the left hand side, you're going to get 2V being equals to the voltage in parallel. That is option C. So the answer to 1.7 is C. 1.8. Which of the following statements best describes resistance in parallel? Let's read and see what makes sense. Option A, adding more resistors in parallel decreases the total current of the circuit. That is not true. And then option B, adding more resistors in parallel decreases the effective resistance of the circuit. We know that to be true, so the answer to 1.8 is actually B. A vector is a physical quantity that has both a magnitude and a direction. A physical quantity that has both magnitude and direction. A good example of a vector is displacement, velocity, and acceleration. While on the other hand, we have a scalar. A scalar is a physical quantity that has only magnitude. An example of a scalar is mass, time, distance, and speed. In 2.2, Peter stands at the front door of his house. Avogadro Street is 25 meters away from the front door. Peter walks to Avogadro Street and back to the front door of his house. So he walks to the street and then walks back again to his house. The first question, 2.2.1, what is the distance that Peter has walked? So we need to be asking ourselves, is distance a scalar or a vector? Distance is a scalar. It only has magnitude. It is defined as the total length of the path taken from one point to another. The total length of the path taken from one point to another. In our scenario, Peter goes from the house to Avogadro's Street. What is the distance from the house to Avogadro Street? That is 25 meters. And then again, he goes from the street back to the house. That is another distance of 25 meters. The key word here is distance. So the total distance that Peter has traveled will be equals to the 25 meters from the house to the street plus the other 25 meters from the street to the house, which will give us a total of 50 meters. So this is the distance that Peter has traveled. What about the displacement? Is the displacement also 50 meters? Bear in mind that the distance is a scalar and the displacement is a vector. That is 2.2.2. The question is saying, let's write Peter's final displacement. So let's just remind ourselves what displacement is. The displacement is the change in an object's position. It is not the total distance traveled or the length of the path taken. No, it is the change in the object's position. So Peter starts at his house, obviously, and then he goes to the street. From the street, he walks back to the house. So what is the change in Peter's position? Peter is exactly where he started. There is no change in his position. So the displacement, Peter's displacement in this case will be equals to 0 meters because there's no change in his position. The distance is 50 meters. because distance is defined as the length of the path taken, but the displacement is 0 meters because displacement is defined as the change in an object's position. Let's look at 2.2.3. Is displacement a vector or a scalar? Give a reason for your answer. Well, at this point, we know that displacement is a vector. And the reason for that is because we have a magnitude for displacement and we also have a direction. If a physical quantity has magnitude and direction, then it is a vector. If it only consists of magnitude, then that's what we call a scalar. You probably know this by now, but anyway, let me just remind you. If you want to convert kilometers per hour to meters per second, you divide by 3.6. And then the other way around, if you want to convert meters per second to kilometers per hour, you multiply by 3.6. And we are going to use that to answer 3.1. The question says that let's convert 135 kilometers per hour to meters per second. Again, to convert from kilometers per hour to meters per second, you divide by 3.6. So let's go ahead and do that. 135 divided by 3.6 is equals to 37.5 meters per second. So instead of having kilometers per hour, we now have meters per second by just dividing with 3.6. Let's move to 3.2. Determine the velocity of car B while trying to avoid car A. Let's go through our scenario so we can see what is happening here. Car A, driving at 135 kilometers per hour, approaches a stationary car B. The driver of car B notices that car A is approaching him at a very high speed. The driver of car B reacted suddenly by accelerating his car from rest at 1.5 meters per second squared for 11.5 seconds. After 11.5 seconds, car B continued driving. Right, so 3.2 again, determine the velocity of car B while trying to avoid car A. We're going to use equations of motions here, but before we decide which equation we are going to use, we need to know which information we have. It is the information we have that is gonna guide us towards the right equation to use. So what do we have here? We have an acceleration of 1.5 meters per second squared. We have time, delta t, which is equals to 11.5 seconds. We have an initial velocity because we are told that the car starts moving from rest. So the initial velocity vi is equals to 0 meters per second. So you need to remember that every time when a vehicle starts moving from rest, then the initial velocity is 0 meters per second. What we are looking for is vf. We have 1, 2, 3, 4 equations of motions. So let's go ahead and find out which equation we can use. Let's look at equation 1. So in equation 1, we're looking for VF. We have VI, which is 0 meters per second. We have an acceleration and we have the time. So we need to go no further because we can see that equation 1 has all the variables we have. So let's just go ahead and use that equation. So we say that VF is equals to VI plus A delta T is the equation we are going to use. And then the velocity final will be equals to the initial velocity, which is 0, plus the acceleration, which is 1.5. The acceleration is 1.5 meters per second squared, multiplied by the time, which is 11.5. If you put that in your calculator, you should get a final velocity of 17.25 meters per second. And this right here, it is the answer to 3.2. Let's look at 3.3. But let's take our equations of motions with us because we might need to use equations of motion in 3.3. Right. So the question is saying, how far has car B driven after 11.5 seconds? So again, let's jot down our information. We have delta t, which is equals to
11.5. We have our initial velocity, which is equals to 0. We have our final velocity, which is equals to 17.25. We're looking for delta x. Let's go to our equations of motions and see which one we're going to use. If you look at equation 1, we don't have delta x. So we cannot use that equation, because how are we going to get delta x when the equation itself doesn't even have delta x? And then in equation 2, we have delta x, which is what we're looking for. And then VF, we have it. We have VI is 0. 2 is a constant, and we have delta t. So as you can clearly see, we are going to use the second equation because it has the variables we have and are looking for. So every time when you're solving this kind of questions, you jot down your information and then guide it to which equation of motion you're supposed to use. So now we're going to say that delta x is equals to VF plus VI divided by 2 multiplied by delta t. So delta x will be equals to, what is VF? VF is 17.25. We calculated it in the question above, plus VI, which is equals to 0. Everything divided by 2. Multiplied by delta t, which is 11.5. If you put that in a calculator, you should get delta x being equals to 99.19 meters. Well, displacement is a vector, so let's give a direction. If we agree that this is west and this is east, we can say that that is 99.19 meters to the east. Let's do the same for 3.2. Our velocity final is 17.25 meters per second to the east. That is because velocity is a vector and not a scalar. Right, let's move to 3.4. The driver of car A suddenly hit the brakes and managed to stop after 40 meters. What acceleration does car A experience to come to a standstill after 4 seconds?
Let's conceptualize. Let's try envision what is happening here. So the car A was traveling at a velocity of 37.5 meters per second to the east. So the initial velocity is 37.5 meters per second. And what is being said here in 3.4 is that in 4 seconds, the car comes to a stop. It comes to a standstill. So at 4 seconds, we have a velocity of 0 meters per second. But then at the same time, during that 4 seconds, the car covers a distance, or it has a displacement of 40 meters. So we have 40 meters here. And then this is all happening in 4 seconds. Well, I want to let you know right now that this is actually impossible. There is no way that the car can start with a velocity of 37.5. 4 seconds later, it has a velocity of 0 meters per second and have covered a distance of 40 meters in 4 seconds. It is actually impossible for that to happen. That is why if you use different formulas, you're gonna get different answers, because you can say that VF is equals to VI plus A delta t. We have VF because the car is coming to a stop after 40 meters. Our VF is equals to 0. What else do we have? We have VI. It is 37.5. We have our time, which is 4 seconds. So we can find our acceleration using this formula. But you can also say that VF squared is equals to VI squared plus 2A delta x. If you use this formula, we have VF squared, we have VI squared, we have delta x. You gotta find a different value. The last formula you can use here is delta x is equals to VI delta t plus a half A delta t squared. If you use this formula also, you're going to get a different value, because this equation doesn't make any physical sense. Acceleration is the rate of change in velocity. What are we saying? We're saying that A is equals to the change in the velocity divided by the change in time. That is 4.1. Let's look at 4.2 and 4.2.1. Use the graph to describe the motion of the car in the following sections. 4.2.1, we are interested in the section AB. We can see that at t is equals to 0, our velocity is 0 meters per second. And at t is equals to 20 seconds, our velocity is 10 meters per second. So what can we say about that? How can we describe that motion? We can say that with regards to the velocity increases from 0 to 10 meters per second in 20 seconds. And with regards to the acceleration, we can say that we have a positive constant acceleration. We have a positive and constant acceleration. As we can see in our graph, we have a straight line. If your velocity time graph is a straight line, then that acceleration is constant. In this instance, it is positive because our velocity is actually increasing. That's what we can say about the section AB. Let's look at the following question, 4.2.2. With regards to CD. So at C, we have a velocity of 40 meters per second. At D, we have a velocity of 40 meters per second. So you can see that the velocity is not changing. So with regards to the velocity, we can say that the velocity remains constant. There is no increase or decrease in the velocity in that section. What about acceleration? What can we say about acceleration? What is the acceleration when VI is equals to VF, when velocity remains unchanged? Acceleration is equals to the change in velocity divided by the change in time. If there's no change in the velocity, then the acceleration will be 0 meters per second squared. So we can say that the acceleration is equals to 0. 4.2.3, which section are we interested in now? EF. Let's look at section EF. So at E, our velocity is 0 meters per second. At F, our velocity is 0 meters per second. With regards to velocity, we can say that the velocity is 0. This would imply that the car is at rest. The car is at rest. We started with a velocity of 0 and the final velocity is also equals to 0. So there's no movement. The car is not moving. And what can we say about the acceleration? Obviously, if there is no change in the velocity, then the acceleration will be 0 meters per second squared. Let's move to 4.3. In 4.3, the question is saying that let's calculate the acceleration of the car between D and E. The acceleration of the car between D and E. There's two ways of doing this. First of all, if you have a velocity time graph, you can use the gradient to find the acceleration. If you don't want to do that, then you can just use your equations of motion. But let's do both. Let's use the gradient first, and then we're going to move to equations of motions. If we use the gradient, what we're saying is that the gradient of a velocity time graph is equals to the acceleration. This will be V final minus V initial divided by time final minus time initial. This is the same as saying V2 minus V1 divided by T2 minus T1, which is what you do in math when you want to find the gradient. You say Y2 minus Y1 divided by X2 minus X1. This is exactly what we're going to do here, but the only difference is that our y is velocity and our x is time. So what is the final velocity at E? That is 0 minus the initial velocity at D, that is 40 meters per second. Everything divided by T final, the time at E, that is 60 seconds, minus the time at D, it is 50 seconds. So that will be minus 50. If you put that in your calculator, you should get minus 4. But that minus is just giving us the direction. So we can conclude and say that our acceleration is 4 meters per second squared to the opposite direction. Before watching me do it, can you just pause the video and try using equations of motions to answer these questions using the approach I showed you on the previous questions. If you did that, then you should realize that we have an initial velocity of 40 meters per second and we have a final velocity of 0 meters per second. Another thing we have is the change in time, which is equals to 60 minus 50, that is just 10 seconds. The equation that you use with these variables, if you're looking for the acceleration, is Vf is equals to Vi plus a delta t. So what is Vf? Vf is 0. What is Vi? That is 40 meters per second plus the acceleration multiplied by the time. If we take 40 to the left hand side, we're going to get minus 40 being equals to a multiplied by 10. We're going to divide both sides by 10. If we do that, we're going to get an acceleration that is equals to minus 4. Again, minus 4 is just the direction. So the acceleration is 4 meters per second squared to the opposite direction. We're going to answer this entire question using the law of conservation of mechanical energy. What do I mean by that? The total mechanical energy in an isolated system is conserved. The total mechanical energy in an isolated system is conserved. That is to say that the initial mechanical energy is equal to the final mechanical energy in the absence of external forces. Mechanical energy is conserved. But what is mechanical energy? That is the potential energy plus the kinetic energy. Let's see how this can help us answer this question. Let's look at 5.1. Define the term gravitational potential energy. The formula says the mass multiplied by the gravitational acceleration multiplied by the height. But what does the definition actually say? It is the energy of an object as a result of its position above the surface of the earth. The energy of an object as a result of its position above the surface of the earth. Moving to 5.2. Prove with calculations that the mechanical energy of the cat at point A is 588 joules. The mechanical energy of the cat at point A. So that will be equal to the potential energy plus the kinetic energy. We have already said that the potential energy is equal to the mass multiplied by the gravity multiplied by the height. And then the kinetic on the other hand is half mass velocity squared. So what is the mass of the object? That is 2 kgs. Gravity, the gravitational acceleration, that is a constant 9.8 multiplied by a height. So at point A, we have a height of 30 meters. So we're going to have 30 right here. Plus a half. The mass is 2 kgs. And now we have to worry about the velocity. So if you go through your question statement, you're going to realize that a roller coaster cut of mass 2 kg is released from rest at point A. So at point A, it is released from rest. That tells us that the initial velocity is 0. So we have 0 squared. If you put that in your calculator, you're going to get 588 joules. So the mechanical energy at point A is 588 joules. But if there's no friction from A to C, then we expect the mechanical energy to be 588 joules at any point, because the total mechanical energy of an isolated system remains constant, is conserved. That's what we mean by that. And then 5.3, state the law of conservation of mechanical energy in words. We've already done that. So let's just go ahead and do 5.4. 5.4, calculate the velocity of the cat when it is at point B. Now we want the velocity at this point. We want the velocity at point B. What are we going to use? The law of conservation of mechanical energy. So the mechanical energy at point A should be equals to the mechanical energy at point B, because it is conserved. At point A, we already know what the mechanical energy is. We calculated it in 5.2. It is actually 588 joules. But what about the mechanical energy at point B? We're going to have the mass multiplied by the gravity multiplied by the height plus a half mv squared. The mass of the object, it is still 2 kgs multiplied by the gravity 9.8. But then the height is changed. It is no longer 30 meters but 10 meters. So we're going to have 10 meters. That is the height at point B. Plus a half, the mass is 2 kgs What are we looking for? We're looking for the velocity at point B. Initially, the velocity was 0, but as our object is going down, some of that potential energy is getting converted to kinetic energy. So the velocity of the object actually increases. Right, let's carry on. So we're going to have 588 being equals to 196 plus v squared. If we take 196 to the other side, we're going to get 392 being equals to v squared. We're going to take square roots on both sides to get a velocity of 19.8 meters per second at point B. Let's look at 5.5. 5.5 is saying, how will the mechanical energy of the cut at point C compare with the mechanical energy of the cut at point B? Write only greater than, less than, or equal to. Give a reason for your answer. We know that the answer will be equals to. Why are we saying that? The law of conservation of mechanical energy. What is a transverse wave? It is a wave where the movement of particles of the medium is perpendicular to the direction of propagation of the wave. What do we even mean by that? If your wave is going from west to east, then you would expect the movement of particles to be perpendicular. So as a result, your wave, your transverse wave, will always look like this. While on a longitudinal wave, where the particles are parallel to the propagation of the wave, you will have something like this. The movement here is still west to east. This is the difference between transverse wave and longitudinal wave. In transverse, the movement of the particles is perpendicular to the propagation of the wave, while in longitudinal, the movement of the particles is parallel to the propagation of the wave. Let's look at 6.2. Label the points A, B, and C. Let's go ahead and look at point A. Point A in a transverse wave is what we call a trough. So point A is a trough. For the sake of clarity, this point here that I'm highlighting, this is another trough. And B, on the other hand, B, it is the distance between 2 points that are in phase and consecutive. So the distance between 2 points that are in phase and consecutive is what we call wavelength. So B is one wavelength, while C, on the other hand, is the opposite of a trough, is the opposite of A and B. C is what we call a crest. So at C, we have a crest. So what will be the name of this point right here? That would be another crest, yes, like point C. 6.3. How many time has elapsed while the wave moved from R to T? Let's just get rid of this and look at R to T. So we have R to T. From R to T. From R to T, we have 2 points that are consecutive and are in phase. So we have one wavelength. From R to T, we have one wavelength. So the time taken to complete one wavelength, it's what we call the period. So basically, in 6.3, we are required to calculate the period. How do we calculate the period? If you look at the equation statement, you're going to realize that we are given a frequency of 30 Hertz. And we know fully well that the period is equals to 1 divided by frequency. So this is just going to be equals to 1 divided by 30, which is equals to 0.03 seconds. So that is the time lapsed while the wave moved from R to T, the period of the wave. Let's look at 6.4. Are points R and S on the wave in phase? Explain your answer. Let's look at R and S. R is right here, and S is right here. A lot of people will say that R and S are in phase, but that is actually not the case. They are not in phase. So the answer is no here. Let me tell you why the answer is no. You need to know the condition that needs to be met for 2 points to be in phase. They need to be n multiplied by wavelength between the 2 points. What does that even mean? Let me explain to you. There needs to be a whole number of wavelengths between the 2 points. So if there is one wavelength between the 2 points, then they are in phase. If there's 2 wavelengths, they are in phase. If there's 3, if there's 4, if there's 5, then those 2 points are in phase. We need a whole number of wavelengths between 2 points for them to be in phase. So let's look at R and S. From R to S, we have half a wavelength. So we don't have a whole number of wavelengths between those 2 points. So that's why we're saying that the answer to 6.4 is no. And then your reason should be that R and S are not separated by a whole number of wavelengths. They're not separated by 1, 2, 3, 4 or whatsoever up to 100 wavelengths. They are separated by a half, which is not a whole number. So those 2 points are not in phase. I have a question for you. If 2 points are not in phase, does that imply that they are out of phase? Or there's another condition that needs to be met for 2 points to be out of phase? Let me know in the comment section. Can you please just leave a comment and tell me what you think about that question? Let's look at 6.5. What does the question say? Calculate the speed of the wave. So what do we need to calculate the speed of the wave? Let's look at the information we have. We know that the frequency is equals to, what is the frequency? The frequency is 30 hertz. We know that the period is equals to 0.03 seconds. What else do we know? Let's look at our graph. We can see that the distance between this point right here to this point is 4 meters, right? It's written here. It's 4 meters. I just covered it as I was trying to show you the points. Yeah, the distance between those 2 points is 4 meters. That is the wavelength. Those 2 points have one wavelength in between them. So we can say that the wavelength is equals to 4 meters. The speed of the wave, V, is equals to frequency multiplied by wavelength. So now we can say that the speed of the wave will be equals to 30 multiplied by the wavelength, which is 4 meters. This is equals to 120 meters per second.
What is meant by a neutral charge? Let's talk about that. A neutral charge is a charge where the number of protons is equals to the number of electrons. We would deem a charge that looks something like this to be neutral. We say that the number of protons is equals to the number of electrons. If that is the case, then we have a neutral charge. Let's look at 7.2. Something to think about. We know that positive and positive repels, and we know that positive and negative attracts. But what happens when you have a neutral charge and a positive charge? What's going to happen? Are they going to attract? Are they going to repel? Or are they going to just be stationary? That is 7.3. Let's go through 7.2 first. So in 7.2, the question is saying that let's state the conservation of charge in words. It says that the net charge of an isolated system remains constant during any physical process. The net charge of an isolated system remains constant during any physical process. That is 7.2. The interesting question, 7.3. Briefly explain how the neutral sphere B is attracted to sphere A. So there we have the answer to the question I had posed earlier. If a neutral charge and a positive charge will attract, they will attract. But now we're supposed to explain why that is the case. Sphere A is positive. Sphere B is neutral. Let's have an example of how that can look like. So for sphere A, we can have 4 protons And then for sphere B, we can have 2 protons and 2 electrons. The same number of protons and electrons. This is positive and this is neutral. What is going to happen when we bring them close to each other? The positive charge will remain as it is. It will remain as it is. Instead of saying N, let's say neutral, because N can also mean negative. So let's say neutral. So when you bring a positive charge and a neutral charge, the electrons on the neutral charge will move closer to the positive charge, while the protons will move further away. This is going to happen because positive and positive repel, right? That is why the protons are further away from the positive charge and the electrons are closer to the positive charge. So what is occurring now here on our neutral charge is what we call polarization. So the positive charge and the electrons are going to be attracting each other because unlike charges attract, but then the positive charge and the protons are going to be repelling each other. But you can see that the distance between the positive charge and the electrons is shorter than the distance between the positive charge and the protons. As a result, the force of attraction will be greater than the force of repulsion. And that is why A and B are going to attract each other. Let's look at 7.4. Calculate the magnitude on the charge of sphere B. What's happening here? Let's go through our equation statement. So in our equation statement, sphere A is brought near the neutral sphere B. And the spheres are allowed to touch each other. Immediately after touching, sphere B moves away from sphere A. Sphere B now has an excess of 20 electrons. So now we have an excess of 20 electrons in sphere B. To calculate the magnitude of the charge in sphere B, we're going to say that Q, the magnitude of the charge, is equals to N multiplied by the charge of an electron. So what is N? We know that we have 20 electrons in excess multiplied by the charge of an electron. That is minus 1.6 times 10 to the minus 19. If you put that in your calculator, you shall get minus 3.2 times 10 to the minus 18 columns. 7.5, what do we have in 7.5? Calculate the charge on each sphere after they have separated. So in order to find the charge on each sphere after separation, we have a formula for that. We say that Q nu, so we have Q nu, which is equals to Q1 plus Q2 divided by 2. Q1 and Q2 being the initial charges on the sphere. So I have a question for you here. Before they touch, we have 2 nanocolumns and 0 columns, right? But in 7.4, we just calculated the magnitude of the charge on sphere B, and we see that that is minus 3.2 times 10 to the minus 18 columns. The question now is to calculate Q nu. Do we use these 0 columns or do we use minus 3.2 times 10 to the minus 18 columns? And why are you saying so? Can you please just let me know in the comments?
What is the reading on V1? V1 is a voltmeter connected across the ends of a battery. In our equation statement, we are told that each cell has a voltage of 1.5 volts. So how many cells do we have in our setup? We have 1, 2, 3, 4, 5 in series. So V1 will be equals to 5 multiplied by 1.5. This is equals to 7.5 volts. This is only true because our cells are connected in series. If they're connected in parallel, then the reading in V1 was going to be just equals to 1.5 volts. You need to know that. Let's look at the second question, question 8.2 and 8.2.1. Let's calculate the total resistance of the circuit. So the total resistance, that is RT, R total, it is equals to RS plus RP. RS being the resistance in series and RP being the resistance in parallel. So let's start with RS. RS, we just simply add all the resistors in series. So RS is equals to R1 plus R2 and so on, depending on how many resistors we have. Here we have only one resistor that is in series. That resistor has a resistance of 2.67 ohms. So that is our RS. Now we need to calculate RP. The formula for that, we have 1 divided by RP being equals to 1 divided by R1 plus 1 divided by R2 plus and so on. In our case, which I don't usually see, we have 3 paths. A proportion of the current will go on this path, and another proportion of the current will go on this path, and another proportion of the current will go on this path. So we're supposed to have 1 divided by RP being equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. If we had a 4th path, then we would have 1 divided by R4. So 1 divided by RP will be equals to 1 divided by the total resistance on the first path. Let's take this as our first path. So that is going to be 1 divided by 6 plus 1 divided by R2. This path, that will be 1 divided by 4 plus 1 divided by R3. That is going to be 3 ohms. So we are going to have RP being equals to 1 divided by 6 plus 1 divided by 4 plus 1 divided by 3 to the power minus 1. This is just 1.3 ohms. So again, RT, it's RS plus RP. We say that RS is 2.67 and RP is 1.3. If you add that, you will get 3.97 ohms. That is the answer to 8.2.1. Let's look at 8.2.2. We need the reading on A1. A1 is this ammeter right here. That ammeter registers total current, the total current that goes through that ammeter. So what does that mean? That means that the reading on A1, we basically need to find the total current. What is the total current equals to? The total voltage is equals to the total current multiplied by the total resistance. The total voltage, you calculated it in 8.1, it is 7.5 volts. IT, the total current, the reading on A1, which is what we're looking for, multiplied by the total resistance, which is 3.97. So now what we're going to do, we're going to divide both sides by 3.97 in order to find our I total. If you do that, you're going to get IT, your total current, being equals to 1.88 ohms. And that is the answer to 8.2.2. 8.2.3 on the other hand, we are looking for the reading on V2. So let's look at V2. On V2, we have the resistance. It is 2.67 ohms. But we know the current that is going to pass through V2 is what we calculated in 8.2.2. The current right there is going to be 1.88 ohms. So in order to find the reading on V2, we're going to say V2 is equals to I multiplied by R. We know that the current there will be 1.88 and the resistance is 2.67 ohms. If you put that in your calculator, you're going to get a voltage of 5.01 volts. The answer to 8.2.3. 8.3, determine the magnitude of the charge that flows through A1 in 6 minutes. So what are we looking for? We're looking for the magnitude of the charge. We're looking for Q. What do we have? We have the current that goes through A1. That is 1.88 amps. And then we have the time, delta T, is equals to 6 minutes. But we know in physics, we don't use minutes, but we use seconds. So let's convert that 6 minutes to seconds by multiplying with 60. So 6 multiplied by 6, that is 36. You just put the 0 on them and you have your time being equals to 360 seconds. Now what you need to recall is the definition of current, the rate of flow of charge. So the current is equals to Q divided by delta T. What is the current? 1.88. It is equals to Q divided by delta T, which happens to be 360 seconds. If we cross multiply, we're going to get Q being equals to 676.8 coulombs.